Hey guys, welcome to day 7. Good job today struggling with and battling through that limit definition of a derivative. I told you it'd get easier, and here it is. Before we get there, I want to talk about different notation that you might see for derivatives. I'll try and use all of these different notations so we're used to seeing all of them. The first one that we know is f prime of x. Again, this means the derivative of So you've seen that in the last video. We saw it today in class. Another notation is dy dx. And again, that means the derivative of y. With respect to x. So again, if something is written as like y equals 3x squared plus 5, if we want to do the derivative, we'd probably write dy dx, because the function was written originally in terms of y. If a function is written as f of x equals 3x squared minus 5, then for the notation for derivative, we do f prime of x. If we have just an expression in terms of x and we want to do the derivative, you'll see the same notation dy dx just without the y. Okay, we won't always use y's and x's. Sometimes we'll use t's, right? So if you see d dt, right, that means the derivative with respect to t. We'll see that when we have problems involving time and things like that. But those are kind of our main notations. Okay, so maybe you guys started to notice the pattern today a little bit in class. But let's talk about it. Let's put it out there. And here is the official power rule of derivatives. We can't use this necessarily all the time, but we can use it a lot of the time, and it's very helpful for us. Eventually, it'll become second nature to you. Okay, so let's talk about the power rule. Okay, so the power rule applies when we have something in the form ax to the n. So again, this works when a and n are constants. A and n can be really any number, and this is going to work. So if f of x equals ax to the n power, if you remember, when we had x squared, we ended up with 2x. When we had 3x squared, we ended up with 6x. When we had negative 4x squared, we ended up with negative 8x. Here's what we get. We always take that power, so in this case the power is n, and we multiply it by the coefficient a. So I'll just call that an. So we multiply coefficient a with power n, and then x, right, the derivative always reduces the power by 1. So, right, if the power was 5, it's going to drop to 4. If the power was 10, it's going to drop to 9. If the power is n, it's going to drop to n minus 1. Okay, so this is a big rule. Again, it's written in a general sense here. But this allows us to solve polynomial derivatives, quite a few actually, in a much easier sense. So let's try a couple of examples. Okay, so if f of x equals 7x to the fourth power, find f prime of x. So I see that f of x here is an ax to the n power, a being 7, n being 4. So f prime of x, then, all I have to do here is take this power, multiply it by the coefficient. 4 times 7 is 28. And it's going to be x to the n minus 1 power. So 4 minus 1 is 3. I'm done. Super simple. Let's try another one. We can see here I'm using that other notation, dy dx, because I wrote the original equation as in terms of y equals 4/3 x to the 6th power. So again, all I have to do here is multiply the power by the coefficient and reduce the power by 1. So using this new notation, everything is basically exactly the same. But instead of writing f prime, I'm writing dy dx. So now I have to do 4/3 times 6. X, and my new power, again, you have to reduce by 1, would be to the 5th power. Simplifying this out a little bit, I can cross cancel. Both of these divide by 3, and I can get a final answer of 8x to the 5th power. And there's my simplified answer. Okay. Let's look at some more interesting ones that may not appear to work. Okay. So when I look at this, I see 10 over x squared. Uh-oh. We've got division, right? Or we see a fraction here. How am I supposed to find f prime of x now? Well, again, the problem is f of x right now is not written in ax to the n form. But the reason you learn about exponents and all that stuff in Algebra 1 and Algebra 2 and pre-calc is so we can make an adjustment here. We know that that x squared here that's written in the denominator, we know that that can be written in the numerator with the 10, right? So I think of it as like throwing the x squared up top. When we do that to make the adjustment, we just have to remember that the power switches signs. So when you see something like this, first put it in ax to the n form. So let's rewrite. Now, by rewriting this thing, I am not doing the derivative. The most common mistake students make is they say f prime of x equals 10x to the negative 2. And they think they're done, but they didn't change f of x, or they just changed forms. They didn't do a derivative. So when you rewrite, it's very important that you can continue to remind the people looking at your work, including yourself, that I have not done a derivative yet. Notice, this is just f of x equals 10x to the negative 2. 10x to the negative 2 is exactly the same as 10 over x squared. Okay? So please note that I'm just rewriting f of x. So now it's in ax to the n form. A is 10, n is negative 2. Now I can go and do the derivative, right? Because it's in ax to the n form. And I can multiply power by coefficient. So negative 2 times 10 is going to give me negative 20. X Please don't say -1 here. Right? We have to reduce the power by 1. -2 minus 1 is -3. Okay. Now, that is a perfectly correct answer for f prime of x. However, if it's a multiple choice type question, they generally write the answer in the same form that the question was written. Notice the question was written in terms of positive exponents. So it's going to be important to be able to go back and convert this thing to have positive exponents. I can take that x to the -3rd power, throw it down to the denominator, and think of it as x to the +3rd power. It's important to be able to do this, right? You may say, well, what's the difference if they're both right? I agree, okay? But if I ask you to find f prime of 2, it's much easier without a calculator to evaluate f prime of 2 in this form than it is in this form, right? What's 2 to the -3rd power? Well, you might struggle a little bit with that. What's 2 to the 3rd power? I hope we don't struggle with that. That's 8, right? So f prime of 2 here would be -20/8, right? And we can reduce that to -5/2. Okay, but much easier to evaluate without a calculator by hand with positive exponents. Okay, let me look at one more example. So here we see g of x equals root x, and find g prime of x. Now, once again, you might say, well, I don't think the power rule applies here. But the power rule does apply here, okay? We just have to think of g of x as in ax to the n form. So again, right, in pre-calculus, you learned about, and algebra 2, you learned about square root being the 1/2 power. So we can again rewrite, and I'm rewriting g of x, so please don't put g prime of x yet. I have to get into ax to the n form first. Okay, and I know that this means x to the 1/2 power. Okay, root x and x to the 1/2 power are identical. They're the same thing. It's just easier to do the derivative from the 1/2 power form. Now you may say, well, what would a be here? Well, again, what's the coefficient that's not written, that's out in front of the x? Well, that would be the number 1. Okay, so now we're ready to do our derivative. And we can say, so g prime of x, I take my power and multiply by the coefficient. Half times that invisible 1 is half x, and then I have to reduce the power by 1. Well, half minus 1 is -1/2. Now, once again, we notice that our problem was written in root form. Our answer has a negative rational exponent. Okay, so the first thing I want to do is take that negative power and put it down into the denominator. Now, if you notice, 2 is already in the denominator. So I can rewrite this thing as 1 over 2x to the half. So I fixed the problem with negative exponents, but I still have a rational exponent. We can now convert back into the form of radicals by calling this 1 over 2 root x. We get g prime to be 1 over 2 root x. Again, all three of these are equivalent answers. However, if you're not going to be using your calculator and you're going to evaluate, this answer is going to be much easier to evaluate. Now take a look back. In class today, we looked at the same thing and we did it by limit definition. And notice we got that same answer, 1 over 2 root x. Okay? But I'm thinking that you probably will enjoy the power rule much more. Okay, couple of things. What if the power is to the first? We have y equals 8x, find dy dx. Okay, well, again, that's in ax to the n form. The invisible n here is the exponent 1. So we could just do the power rule and say, okay, dy dx then. I'm going to take this invisible 1 and multiply it out front. And I'll have 8. And then I have to reduce the power by 1. Well, what is that x to the 0th power? Well, any number other than, I guess, 0 to the 0th power is always equal to 1. We just get 8. Okay? We just get 8, which brings us to a rule. If we have f of x equals a constant times x, c being any constant. In the example 5, it was a constant 8. So if we have cx, then f prime of x would equal c. Okay? Well, what if we just had a constant? Right? There were constants in some of the examples that we worked on today. Well, the derivative of a constant, let's take a look at that example really quick. Well, we can kind of reason this out in a few different ways. Well, let's think about the function y equals 7, or f of x equals 7. That would be a horizontal line at 7. F prime always gives the slope of the tangent line. What is the slope of the tangent line to any point on a horizontal line? Well, it would always be 0. Here we have so again, another rule. If f of x is equal to a constant, it doesn't matter if that constant is 7 or 10 or pi or e. Okay, the derivative of a constant is always 0. Okay. If you wanted to, you could think of that 7 in example 6 as 7x to the 0 power. Take that exponent of 0, multiply by 7, and the whole thing is 0. Okay, so the derivative of a constant is always 0. Our very last rule. If we have, let's say we're saying f of x equals g of x, either plus or minus h of x. So let's say we want to do the derivative of a couple of functions added or subtracted together. Okay, doesn't matter how many there are. Okay, the derivative then, we just do the derivative of the first, and then if it was plus, we have plus. If it's minus, we use minus. The derivative of the second. That's it. So let me give you one more example for that. I think this is example 7. Let me change one of those to minus. Sorry. So if I want to do the derivative of a string of functions added together, like a polynomial, very simply, I can just go through and do the derivative of each one. So f prime of x then These are all in ax to the n form. I'll just start with, well, that would be 12x squared for the first derivative plus 28x to the first. All right, I don't need to write that to the first because we're in AP calculus. And then what's the derivative of -5? Well, that's a constant. I know the derivative of a constant is always 0. You can write plus 0, or you can just not write anything. And there we go. So when you have several things added or subtracted together, just go along and do the derivative of each one. All right, that's it for today. Make sure you watch this and you're ready to go to practice this on Monday. Talk to you guys later. Bye.